Hi, so this video is going to cover section 4.3 properties of logarithms for college algebra. Um, so in the notes, what we're going to do is go through some, as you can imagine, some specific different properties of logarithms that are going to be helpful to us when we solve equations, which will be the next section. So what basically how this is presented is we look at an exponent rule and look at how that relates to logarithms, because remember a logarithm is an exponent, right? So those properties are going to mimic properties of exponents that you would have learned previously to this course. So for this first one, we want to look at the product rule. So if you remember, if we multiply bases, two things together with the same base, then we add its exponents, right? That's what this is showing, right? So if you have b to the m times b to the n, this is equal to b raised to the m plus n, right? The addition of the exponents, right? So like, just so that way if we have like x cubed times x to the third, right, this is equal to x to the fifth, right? Because we add together 2 plus 3 to get to the fifth power, right? This is a pretty common rule that we use throughout throughout algebra, multiplying polynomials together and such. So I won't do this for all of them, but for the first one, I want to go through a pretty formal proof of the product rule, and that way you can really see that these two things are connected: logs and the properties of logs and the exponent properties, right? Now you can do this for all of them. I won't, just for time's sake. The product rule for logs, right, says that if we have b, m, and n are positive real numbers and b cannot be equal to 1, then if you have the log base b of a product, you can split this apart in as addition, right? So you have log base b of m plus log base b of n, right? So we're able to show that as a sum of logs. So the log of a product is the sum of the logarithms, right? That last statement. So what we can do is, let's let x equal log base b of m, right? And y equal log base b of n, right? So then from those two statements, right, what we can do is I could rewrite each of those in its exponential form, right? So x equals log base b of m is equivalent to, right, the same as, so this is just a symbol like double arrows, right, meaning equivalent to. We can go back and forth between the forms. This would be b to the x equals m, right? That's what this means, right? There's my base, there's my exponent, and that's what the whole thing equals, is m, right? And then also y equals log base b of n is equivalent to b to the y equals n, right? So now what I want to do is take m times n, right? So m times n is equal to b to the x times b to the y, right? So just substituting those in, right? M is b to the x and n is b to the y, right? So now that I have two things being multiplied together with bases, I can use that exponent rule that we just reviewed, that this is going to be equal to b to the x plus y, right? The sum of the exponents, right? Right? So what we have is that m times n equals b to the x plus y, right? This is equivalent to it would be log base b of mn equals x plus y. Right? So these two things are equivalent. So I just took this expression in exponential form and rewrote it in the logarithmic form. Right? So log base b of mn equals x plus y. So now what I can do is I know what x equals, right, from this, and I know what y equals here. I can plug those in for x plus y, and what we have is our rule, right? So this means that log base b of mn equals log base b of m plus, so plus y, which is log base b of n. Right, so all I did was substitute in for x and y into this expression, or this equation here, and came up with this, right? Which is exactly what we were trying to show, right? So these two things, both sides must be equal, right? This is a direct proof, right? We're able to directly prove that that property is true, right? Using exponent properties. So it's helpful to rewrite in exponential form, look at the exponent properties, and then put it back in terms of logarithms, right? Essentially what we did. And like I said, you can do that with all of these properties if you kind of want to explore how all these are working, right? So then what I have here is an example just practicing that notation, right? So for part A, we have log base 4 of 7 times 5, and we're asked to expand each logarithm out using the product rule, right? So since we have a product going on, right, that's the sum of the logs, right? So we keep the same base. So this would be log of 4 of the first factor, 7, right? And then plus log base 4 of the second factor, which is 5, right? And something else I would caution you to do is just to put parentheses around what you're taking the log of, just to make that clear where it starts and stops. Because you'll also want to do that when you put it in your calculator. Right, so it's good to get in the habit just so it's clear notationally and so forth. All right, so that's all we can do for that one. And then for part B, I have log of 10x. Right, so don't forget, since there's no base written, that means it's understood that it's the common logarithm of base 10. Right, so this would be equal to log of 10 plus log of x, right, using that product rule. And then we can use use a property we learned in a previous section about logs, where we can simplify log of base 10, right? So, or excuse me, log of 10. So if we're taking the log base 10 of 10, so that's just 1, right? This is just 1 plus log of x, right? So log of 10 is just 1 is what I'm noticing, right? Because what you're asking for is, I can fill in a 10 here. You're saying if I have a base of 10 raised to some exponent, right? We don't know what that is. It's going to be equal to 10. What's the exponent going to be? Well, of course, it's just going to be 1, right? Because these are going to have to match. If you have the same bases equal, their exponents must match, right? So anytime, remember I showed you before that if you have, let's say, a to the u equals a to the v, then u must equal v, right? We know this fact. Right? So since we have the same, so we use the same variable here, right, to denote that they have the same base. So like in this case, I have 10 to the first on the right and 10 to some exponent we don't know. Well, it has to be 1, right? So that's what that answer is, right? All right, so then the next rule to look at is the quotient rule. So if you remember, right, when you divide two things of the same base, we subtract their exponents, right? So you can see the exponent rule here just as review. So it's called the quotient rule for exponents. So the quotient rule with logs is very similar, right? In that we're going to subtract, right? So it's very similar to the product rule we just looked at, except you'll see in here that we have a quotient. We have two things being divided, and we can break those apart with subtraction in between, right? So that's the quotient rule. So the logarithm of a quotient is the difference of the logs, right? So as before, let's walk through an example just to practice this. So I have log base 7 of 19 over x. This is equal to log base 7 of 19 minus log base 7 of x, right? Again, I'm just going to put parentheses around this to make it clear. And there's really nothing else we can do with that, right? So we can just leave that alone. And then part B, we have the natural log of e cubed over 7, right? So this would be equal to the natural log of e cubed minus the natural log of 7, right? So I can actually work with this first part, the natural log of e cubed, right? So, if you're wondering, like, well, Tyler, how do I, Professor Maley, how do I know exactly when I can, like, simplify this further? Like, how do I know I can't simplify one of these from part A, right? One of these logs. Well, this one sticks out to me in part B because I'm taking the natural log. The natural log is base e. And then I'm taking the natural log of e raised to some exponent, right? So immediately should be thinking like, oh, I can simplify that, right? So this is one of those cancellation properties that we looked at previously. This is going to be just the exponent that's left, so just cubed, right? And then you'd have minus natural log of 7, right? And something else, just to note and emphasize, is whenever you have the log of a constant, right? So when I'm looking at this is just a number, right? So when you see something like this, you should be thinking, if I make like a thought bubble, right? You should be thinking when I see natural log of 7, that that's just some number. So that's going to be helpful when we solve exponential and logarithmic equations, just to remember that. So that way when we're solving the equation, we can add, subtract, multiply, divide by like natural log of something, because it's just a number. It's going to be most likely an irrational number, but it's going to be a number, right? And then also don't forget, let me just change color here, that the natural log of e cubed, if you don't remember those cancellation properties, right, we can investigate like we did before. So let's say I don't know what the natural log of e cubed is, but I'm like thinking to myself, this should reduce down. I could just let this be equal to some variable, let's say, I don't know, a, capital A. So then if I rewrite this in exponential form, right, what this means is e to the a is equal to e cubed, right? So then using that previous note from above, right, so this fact, right, so using that fact, I know that these exponents must match, right? So in other words, a must be 3, right? So therefore, this we can just plug back in, right? A is just 3. So this natural log of e cubed is just 3, right? So that's how I know that this is just going to be 3, right? So we get 3 minus natural log of 7. All right. So then we want to look at another rule, the power rule. So this is actually one of the this is going to be a rule that we definitely use a lot, so I would definitely understand the power rule for logarithms. So we have here, like you would guess, just review of what we mean exponentially, right? So if you have something raised to a power and that whole thing's raised to a power, like that's shown here, So we have a base b raised to the m power, and then that whole thing's raised to the n power. Then we multiply those together, right? So for example, if you had like x squared cubed, this is equal to x to the sixth, right? You take 2 times 3, right? So a power to a power, you multiply. So that's known as the power rule. So with logs, right, this is going to be a really useful fact, is that if you have the log of any base of some expression raised to an exponent, notice what you can do is take that exponent and pull it out in front as a product, right? So in other words, you're just noticing that I can multiply, like here with this exponent rule, we're noticing that I can just multiply those exponents together, right? Because remember, you know, again, when you see this log of something, you should be thinking of that's an exponent, right? So I have p, which was an exponent, times another exponent. So it's, you know, that's how it's related to this rule, right? Right. So something else to review really quick is when you have you know, radical signs. So like if you have like a cube root, square root, and so forth, you know, how do you rewrite that as an exponent, right? So the general rule of thumb, right, if I have the nth root of x, let's say, this is going to be equal to x to the 1 over n, right? And it's understood that if you just have the square root, that there's really an index of 2 here, but we just don't write it. It's just understood, right? So whenever you have just a square root symbol, it's like a second root, right? Taking the square root, right? Well, I guess that n isn't drawn very in the right spot, is it? I didn't mean for it to look like it's like times. So I want it to be up there in the index position, right? All right. So let's go through this example and practice this. So if we look at part A, we have log base 5 of 7 to the 4th, right? So using this rule, right, what I'm able to do is take this, so I'm going to put parentheses around this, take this exponent and just put it out in front, right? So this is going to become 4 times log base 5 of 7, right? Part B, I have the natural log of the square root of x. So in order to work with this one, you want to rewrite x with an exponent. So this would be natural log of x to the 1/2 power. So this, right, I can take that exponent, pull it out front as a factor, right, using the power rule property. So this would become 1/2 times the natural log of x, right? And then part C, we have the common logarithm, right, log base 10 of 4x all raised to the 5th power, right? Notice the whole thing is raised to the 5th power. That's important, right? So since the whole thing's raised to the power, I can pull out the 5, right? If it was not the whole thing raised to the power, so in other words, if it was log of 4x to the 5th power, I couldn't just pull that 5 out in front, right? It has to be the whole expression raised to the exponent. I mean, something I could do is use the, product rule and split these apart and then apply the exponent rule. And we're going to practice some of those. But I just wanted to emphasize that, right? So since this whole thing that we're taking the log of is raised to the exponent, that's what allows us to pull that out in front, right? So this is just going to become 5 times log of 4x, right? So then at the bottom of this page is just a nice table just putting all of those rules together and just kind of a nice easy format, right? And of course here it's saying that m and n have to be greater than 0, right? Because remember that's the domain of a logarithmic function goes from 0 to infinity, not including 0, right? And of course not including infinity. All right, so what we want to do for for part 4 is just to practice those properties. We're going to use more than one at a time. And we want to try to, in this case, we want to try to expand these as big as possible, right? And then, as you could imagine, what we want to do next is the opposite. Start with kind of this expanded form and try to condense it down as much as we can, right? So the goal here is just to get more acquainted, more comfortable with these properties. So part A, we have log base b of x squared square root of y, right? So looking at this, the first thing I would notice is I have a product, right? I have x squared times the square root of y. So that's the first thing I'm going to do is split these apart with sums, right? So using this product rule right down here, this very first one we learned. So this would be log base b of the first factor plus log base b of the second factor, which is square root of y, right? And then what I can do, excuse me, is I can rewrite square root of y as y to the 1/2, right? So this would become log base b of x squared plus log base b of y to the 1/2, right? So then now what I can do, right? So now what I can do is use the power rule, right, and pull those exponents out in front. So I can take this exponent, pull it in front, and take this exponent, pull it in front, right? So what I end up getting is 2 times log base b of x plus 1/2 log base b of y, right? Again, if we want to just emphasize, just for clarity, of what we're taking the log of, right? All right, so let's try the next one. Let me use a different color just in case this will run together. Go back to red. Well, and this one's actually going to take quite a bit of space, so I'm going to just come off to the side to work this one. All right, so for part B, what we have is log base 6 of the cubed root of x all over 36 y to the 4th, right? Yeah, and just to emphasize, I don't know why I keep making the index so large. Right, this is the cubed root, right? Log base 6 the cube root of x over 36y to the 4th. Right, good. So really, like, thinking about this big picture, what you should notice is I have, this is, looks like a fraction, right? It's a quotient. I have something divided by something. So that's the first thing I would do to tackle this, is to split this up, right, using that quotient rule. So we do it with a subtraction, right, a difference. So we'd have log base 6 of the cubed root of x, right, minus log base 6 of 36y to the 4th. Right? And just as I pointed out before, it's important to note that I can't just pull this 4 out in front because the whole expression is not raised to 4th power, right? This term is not raised to the 4th power. Right? So what I would do next is, one thing we could do that I see is we could rewrite this using an exponent of 1/3 to x, and then this is a product, so we can split those two things apart as sums, right? So what we would have is log base 6 of x to the 1/3 power, and then we'd have minus, and this is important, I'm going to put brackets like around this, because I'm going to split this apart in two terms, and we need to subtract both terms, right? So that's going to be real important. So this would become log base 6 of 36 plus log base 6 of y to the 4th. right? So now you can see that, the subtraction, this also has to be negative, right? So both of these terms are negative. So if I change this to addition, distribute that negative through, both of these, both this term and the second term become negative, right? So you might have made an error there if you wouldn't have recognized that, right? So then now what I can do for this first one is I could pull out the 1/3. So this would become 1/3 log base 6 of x. And then, we would have minus log base 6. And one thing you'll notice is that 36 is 6 squared. So that sticks out to me because we're dealing with base 6, right? So let me rewrite 36 as 6 squared. And then we'd have minus, and we can pull here, for this term, I can pull out the 4 out front. So this would be minus 4 times log base 6 of y, right? So I think the only thing we can do now is just reduce down this middle term, right? So this is one of those cancellation properties again. So what that's going to do is we're going to be left with just 2, right? Just the exponent. And we've done some similar examples like that, right? So this would become 1/3 log base 6 of x minus 2 minus 4 times log base 6 of y. Right? So that's part B. Right. So now what we want to do is go in the opposite direction. Right? So so for part A, we have log base 4 of 2 plus log base 4 of 32. Right? So one thing you can notice is that these have the same base, and we're adding them. So that means that this is the product rule, right? So I'm able to rewrite this in one logarithm. So log base 4 of 2 times 32, right? So really, I guess that's the directions. We satisfy the directions. It just says take the thing and write it as a single logarithm, right? So we've done that. We've rewritten the given information just as one logarithm. But this one is, interesting enough, we can keep working it through and actually come up with some constant value, right? So let me show you what I mean. So I can rewrite this as log base 4. So 2 times 32 is 64. And then it turns out that 64 is 4 cubed. Right? The reason why I'm interested in this is this has the same base as what we're working with in the logarithm, right? So this would be the same thing as log base 4 of 4 cubed, right? So now I have a cancellation property, so this just becomes 3, right? Just the exponent in that case, right? So part A, this whole thing just equals 3, right? So then part B, we have log of 4x minus 3, and then minus log of x, right? So notice they're both the common logarithm, which means they have the same base, and I'm subtracting 2 logarithms, right? So that's the quotient rule. So this would be the log of 4x minus 3 all divided by x, right? There's nothing, really nothing I can do with that, right? So we can just leave that. Right? So then there's some more examples of what we just did. So trying to condense it down, and maybe these maybe are a little harder, right? Maybe did some easier examples, and now pulling in maybe some of the power rule and so forth. So part A, we have 1/2 log of x plus 4 log of x minus 1, right? And also, I just want to emphasize and mention again, it's important to note that in order to use these properties, we have to have the same base in all the logs, right? If they don't have the same base, we can't do this, right? Just like when you have the exponent rules, you can't, like before, you can't use those if they don't have the same base, right? So like if I had x squared times y cubed, that's why we don't add the exponents here, right? They have different bases, so the exponent rule doesn't apply. Right, so I can't emphasize that enough, because in all these examples the bases have been the same, so we've been able to practice that. But don't think you can just do that in any case, right? So we have 1/2 log of x plus 4 log of x minus 1. So I have the same base here, right? They're both common logarithms, and I have the addition between them, right? But I would urge you that we want to work with the exponents first, so using the power rule. Before we try to rewrite this with multiplication, because that can get I think that could get pretty messy if we don't do that first, right? So if I rewrite this using the power rule, this would be log of x to the 1/2, right? So I'm working backwards, right? I'm taking the factor out front and putting it back as the exponent, right? So log of x to the 1/2 plus a log of x minus 1 raised to the 4th power, right? So again, taking the factor and re-putting it back as the exponent, right? So kind of in reverse, right? So then if we wanted, I could rewrite log of x to the 1/2. We could rewrite that as log as a square root of x if you wanted, right? You don't necessarily have to, but we could. And then this would be plus log of x minus 1 to the 4th power. And then now that I have the same base of the log and we're adding them together and there's no factors out in front, right? Now is where it'd be really nice to use that first property we looked at and rewrite it as a product, right? So this would be log of radical x times x minus 1 to the 4th power, right? So this would be the condensed down single logarithm. Right. So of course we're practicing these properties because there's going to be times where it's convenient or necessary for us to be able to condense or expand the logarithms when we're working with them, right? So part B, we have 3 times the natural log of x plus 7 minus the natural log of x, right? So as before, I would first work with these factors and take it as an exponent first. Let's see, and this is a 7, right? So this would give me the natural log of x plus 7 cubed minus the natural log of x. And then we have the same base, right? Base E, Euler's number, and we're subtracting, so we can use the quotient rule. So this would be the natural log of x plus 7 cubed, all divided by x. Right? And that's really all we can do with that one, right? So let me grab another color. Choose black. Let's see, and I'm running out of space on the page here, so let me just go over to the right. Right, so this is part C. We have, let's see, 4 log base B of x minus 2 log base B of 6 minus 1/2 log base B of y. Right. So I'm going to condense this down. So the first thing I would do, work with these factors, put them as an exponent. So this would be log base B of x to the 4th minus log base B of 6 squared minus log base B of y to the 1/2. Right? And I can simplify 6 squared and I can rewrite y to the 1/2 as a square root of y. So let's do that. This would be log base b of x to the fourth minus log of b of 36 minus log base b of the square root of y. Right. So then I'm going to work with these first two first, right? So this would, I could rewrite that as log base b of x to the fourth divided by 36, right? So rewriting using the quotient rule. Right. And then we'd still have the minus log base b of square root of y, right? And then now I could apply the same rule but with those two things, right? So this would become the log base b of x to the fourth over 36 all divided by square root of y, right? But when we divide fractions, right, this would be the same thing as log base b of x to the fourth over 36 times the reciprocal, right, which would be 1 over the square root of y. So the reciprocal of the denominator. So then this gives me log base b of x to the fourth all over 36 radical y. Right? There's really nothing more I can do with that. Right? So there's part C. Right. So then there's another property. We've actually already looked at this. I showed this to you earlier so that way we could graph logarithms in our calculator, right? Because remember, in our calculator we only have two buttons, right? So if I pull over graphing calculator, right, you have a log button, the common logarithm, and the natural log button, right, base E, log. So we only have those two options on our calculator, but we can still work with any log using this change of base property. So this is going to be another one that we are going to use a lot. Whoops. So let me drag that back out of the way. So remember with the change of base property, right, you take, you can change to any base you'd like, and you just take basically, I think of it as b as like bottom, right? It's like below, so that goes in the denominator, right? So if you have log base b of m, that's equivalent to log base a of m divided by log base a of b, where a can be any base that you would like, right? So we, if we look in the next table, right, it's using the common logarithm and the natural logarithm, right? Which makes sense because again, that's what we have in our calculator, and if you think about it long enough, it makes sense that those would be the two that we would want to have, right? Those are like the most common ones to use. So if you have log base b of m, that's equal to log of m divided by log of b, or log base b of m is also equal to the natural log of m divided by the natural log of b, right? So we're going to use these two items a lot, right? So you definitely want to be familiar with those properties, right? You want to be familiar with all of them, but some of those we might use more than others, right? They might come up more. Right, so we just got two last examples here to try with using the change of base formula. So what we're asked to do is evaluate log base 5 of 140 using the common logarithm, right? So log base 5 of 140, right, is the same thing as log of 140 over log of 5, right? So again, visually, I just think of like drawing a line here as like a fraction, right? So this guy goes on top and that number goes on the bottom, right? So I don't know if that helps you. So then we can pull out our calculator and enter that in. So I can do log of 140. Right, you want to make sure you close the parentheses, right? Don't forget that. And then divide by log of 5. Right, and we get this decimal approximation, right? So we get roughly 3.0704, right? So this is roughly 3.0704, right? Then, of course, this would be the same thing. You get the same answer if you took the natural log instead of the common log, right? We just looked at that, right? You can use any base log that you want, and it still works out to be the same, right? So we get the same exact number, right? So that's pretty cool, right? So we were just asked to use the common log in the directions. So then for part B, we're asked to do the natural log, and it's the same thing, right? So I guess I already did this in the calculator, right? So if you do log base 5 of 140, this is equivalent to the natural log of 140 divided by the natural log of 5, right? Which would be equivalent to that 3.0704 number, right? So it's approximately equal to 3.0704, right? And we already did that in the calculator, right? All right, so that's all I have for this section. Thanks.